Let's do it. Good morning, everyone. Good morning. Thanks everyone for coming. It is my pleasure today to introduce Alex Cleveringa. Alex will tell you more about him. He's been here for a while. He'll give you some details, but it's been really fun to have Alex in our research group. Alex, some of the other things that you might not hear about that he's going to talk about today, he was a TA for my undergraduate class. He also TA field plot technique with Ken Moore. I think definitely one of my favorite things about Alex is his laughter. When I was teaching my class, even my worst jokes, it would be at least Alex was laughing.
The only one sometimes.
Alex just has this wonderful laugh that we're gonna miss for sure. So, and he laughs at all my jokes.
And all my committee members' jokes. I mean,
so certainly. Okay. Well, besides that, I'll highlight a few other things about Alex. I think it was last year we had an applied statistics conference year names. Alex presented as a graduate student, and he won first place for that presentation. So it was a great presentation. You're going to hear a little bit of that, what he presented at that time. And I think partly because of that great presentation, he was later invited to go to Florida and present more of his research there, and he had a good experience. I don't think he's going to talk about that today, but I think with that, I'm going to just let Alex take over. Thanks everyone for coming again. Thanks for the committee members. And I hope you guys enjoy the presentation as much as I enjoyed working with Alex.
Okay, thanks, Fernando. So thank you all for being here. I really appreciate it. Does everything look okay on the?
Yeah.
Okay.
See. Can people hear you?
Yes, I checked that already.
Okay, great.
Okay. So like Fernando said, I've been here a long time. This is me as a freshman, a proud member of the Iowa State University Cyclone Football Varsity Marching Band. I got my bachelor's degree here in 2015, got my degree and thought, all right, let's go get a job. Done with school, great. I wasn't done with school. A few years later, I came back and got my master's degree in soil science. And I was finishing that up and said, all right, I'm almost done with school. Let's go get a job. And then I woke up one morning over the summer to an email from Fernando. This is how you get into grad school if you didn't know. You just wake up to emails inviting you. So I thought, well, that's too good of an opportunity to pass up. And so now that brings us to today. They said it's your last, there's nothing after PhD. She's like, well, I better get a minor. Maybe I should get a graduate certificate while I'm here. Just like some side quests along the way. So yeah, I'm excited to be sharing my research, my dissertation with all of you. The title I came up with is Soil Fertility Trials on Trial for Noise, Statistical Implications for Soil Fertility Modeling. So we have a lot of people here who know a lot about soil fertility and some people who know basically nothing, which is great. So we're all gonna hopefully get something out of this presentation. So I'll provide some background information for people who don't know as much heading in, and then we'll get into each chapter of my dissertation. Chapter 2, Losing Control. Chapter 3, the Quadratic-Plateau-Quadratic model. And then chapter 4, Can You Hear Me Now? And then I'll provide a brief summary of the main findings from all of those chapters. So first and foremost, what is soil fertility? We're doing soil fertility trials on trial for noise. Well, first of all, soil fertility is the ability of the soil to support plant growth and productivity. We have a growing global population. We need to provide more food for those people. And when we grow crops, when they're harvested, they remove nutrients from the soil. And so those nutrients need to be replaced so we can continue to support these high yields into the future. The goal of soil fertility research is to find the optimum fertilizer application rate. So the optimal rate is the one that maximizes the efficiency of fertilizer use and at the same time minimizes losses to the environment. Now there's water quality impacts and other effects to the environment when nutrients they leave the field and enter the environment. And farmers don't like that either because they pay a lot of money to put that fertilizer on the field and they want to get the most out of it that they can. So how do we do these trials in this research? Well, the first step is you have to find a soil test. Here I'm showing the Bray phosphorus test, and it's correlated with yield. So as some soil test value, when you sample your field, you get your results back from a soil lab, and they say, okay, here's your soil test value. And as that value increases, you'll see an increase in yield up to some maximal value. Once that's done, they'll calibrate the field for those different soil test levels. So here we can see the medium soil test level, and it starts off when we don't apply any fertilizer, we see pretty low yields, and as we increase the fertilizer rate, we increase the yields up to some maximal value. Another thing that people consider in soil fertility research is finding what the critical level is. So that's some soil test value on the x-axis, where if you're below that and you apply fertilizer, you'll probably see a response. And if you're above that critical value, you probably won't see a response. It's not quite cut and dry like that. So there's some people will do like a probability of a response, where if it's in a very low category, you're extremely likely to see a yield increase. And as the soil test value gets higher, you're less likely to see a response. So that's soil fertility. Now, how does noise come into this? So back in 2020, we read a book in our book club that Fernando hosted in his backyard, because you had to be outside for everything back then. We read this book, Noise, by Daniel Kahneman, and he's the author of Thinking Fast and Slow, a very popular book if you've heard of that. And the main takeaway from this book is that humans, when presented with the same information, can come to different conclusions. So different judges can be presented the same case and arrive at different verdicts or different sentences. Doctors can look at a certain patient and they'll come up with different diagnoses or different treatment plans. Claims adjusters and underwriters, if they're in the tax world, they'll make different adjustments. And it's subjective. There's a lot of variability in these processes. And so how you can think of this visually is there's some signal, which is shown with the red lines. And when there's no noise, which is the blue line, so the figure on the left, it's very clear. We can see the signal, we can see what we're trying to see, what we're interested in. But then as that noise increases, the image starts to get blurry. So obviously we don't have image, we're not looking at an image of our field per se like this, but what kind of noise do we experience in soil fertility? Well, we have soil variability for one. This is from Surgo, the Web Soil Survey of the agronomy research farms here. And you can see there's a bunch of different soil types all within this area that I've highlighted. And this is, for a farmer's field, this is very small. So this scale here is only 400 feet. So if you think of like a production size field, they're much larger than this. So they're going to have a lot of soil variability. There's also a lot of weather variability. So this is 30 years for one of my sites that I'll be talking about later. And you can see the total amount of rainfall that it received every single year could be very different. And the distribution of the rainfall could also be very different. How you sample your soils also can impact your results if you do grid sampling versus zone sampling. There are also different recommendations for how frequently you do your soil sampling, indicated with different colors here. You could sample to different depths, anywhere from 0 to 10 centimeters to 0 to 30 centimeters. Depending on where you send your soil samples, which lab you send them to, you could get different results, adding to the noise. The experimental design you choose can introduce noise, which we'll get into shortly. And then the statistical analysis you do can also introduce some noise. So what do we do with all this noise, all this variability? What do? We do our best, and we do statistics. All right, so that brings me to chapter 2, losing control. What happens when the control treatment is excluded in nitrogen fertilizer rate trials? So I'll provide a little bit more background information for this chapter specifically, and then I'll talk about the analysis that I did. We'll talk about results. We'll do some example fields and then look at what trends we saw overall, and then I'll draw a few conclusions about the chapter. So generally, as I mentioned before, on small plot research, we'll have a number of different rates, fertilizer rates applied in the field, as you can see on the x-axis, this one ranging from 0 to 315 kilograms per hectare, yield on the y-axis, and as we would hope, as you increase your fertilizer rate, you do see a yield response. Next, we'll fit some model to the data. Here we have the quadratic plateau model. The equation is shown here, where you're increasing in with a quadratic function up until some breakpoint where you see a plateau. And so that breakpoint is called the agronomic optimal nitrogen rate. So this is the rate beyond which we don't expect to see an increase in yield. It's calculated with the equation shown. And there's some uncertainty associated with that AONR that we estimate in this experiment with the delta method. So that's when we do small plot research trials here. Now, when we do on-farm trials, this is when a researcher is giving an experimental design to a farmer and saying, okay, go do this. And because they have different equipment, we're oftentimes doing treatment applications by hand and they're using equipment. And so we'll make some adjustments in the experimental design. We'll have fewer nitrogen rates frequently. So the design I showed before has 8 rates, and they'll maybe only do 4 or 6 rates. They'll do a narrower range of rates. So instead of going from 0 to 315, they might go from 120 to 300 or 280, something like that. And they'll exclude the control treatment, that N0 treatment. The reason why they like to exclude this treatment is they get yellow spots in their field and their neighbors see it, and they're not something that they're really proud of. They also know that their optimal rate is not 0. It's almost never 0 for nitrogen. It's usually closer to 200. And so they're like, why would I waste my time applying a rate I know isn't the optimum if I'm trying to find the optimum? It's a fair question. And we also have less control over the experiment because we're not, visiting it frequently. We just give the design to the farmer and say, do this, we'll come back and collect the data when you're done. So next I've got some examples of experimental designs from scientific publications that I found where they're designing these on-farm trials to kind of show you that I'm telling the truth. So here we've got an experimental design, and the main point here is the nitrogen rate range that I was talking about, going from 79 to 129 kilograms per hectare. So they're nowhere close to 0 in just a narrow range. This is another design where the application treatment rates go from 188 to 292 kilograms per hectare. Again, missing the 0. They have a lot of replications though, which is common. This experiment that I found here from this paper, they did go from 0 to 336. They had a great range. They've got maybe 7 or 8 treatment rates, so it looks really good. But what the researchers found is when they fit different models to this data, the optimal rate that they calculated was very different. It ranged from 87 to 173. Now that's not great because you're getting different results with the same data depending on the model you choose. That's a source of noise. And so what they found was if you only look at a few of the treatment rates, ranging from 112 to 224, when they fit some models there, the models fit really well because you only have 3 data points, but the optimal rates also got really close together. So they're like, hey, maybe we should design experiments this way. But what they didn't do is measure the uncertainty of this experiment, and I'd be very curious to see what those results would have shown. Okay, so the type of analysis that we'll be doing is called the leave one rate out analysis, where we'll exclude one nitrogen rate. Here I've got the 0 rate dropped out. We'll fit our model to the remaining data. We'll calculate the optimal nitrogen rate when that treatment rate is excluded. That's that minus N0 subscript is for, and we'll measure its standard error as well. And then we can put the data back in, and we can make comparisons. We can drop the next rate, the 45 treatment out, and we can fit a model and calculate the AONR and do it all over again. All right, some common terms that we'll be using in this presentation today is accuracy and precision. So I've got some targets here demonstrating the difference between those two. I think I'll probably get this tattooed on myself when I'm done with this presentation. I'm not sure yet. But the ideal scenario is the bottom right, where we've got high accuracy and high precision, where all of the points are close together and they're in the middle of the target. That's ideal scenario. You could have a scenario where there's low accuracy, where we're missing the mark by a certain amount, but it's pretty consistently missing in the same amount. So we're not very accurate, but we're highly precise. You could also have a case in the bottom left where you're on average close to the center, but there's more spread than the first example. So that would be highly accurate, but not precise. The worst case scenario is where you're not accurate or precise, where you just kind of got data points all over the place. So we don't want to see that one. How we assign numbers to these ideas. So bias is generally calculated as the estimate minus the true value. Now, if we knew the true value, we wouldn't have to do an experiment. We could just go home. I wouldn't have a job. Well, I'd have a different job, I hope. But anyway, so we consider the true value to be the value we get when we use as much data as we have available to us. So that's using all 8 rates. That's as close as we can get to the true value. And then we calculate the difference between the full value and when we've excluded each treatment rate. When we calculate precision, I'll do the words first and then show the equations. So we know that there's some standard error associated with the estimate when we use all 8 rates. That's just built into nature. And so what we're interested in is how much does that precision change? How much does the standard error change when we drop each individual rate? And so we're comparing on a percentage basis the difference between the full estimate standard error and the standard error when we're excluding a treatment rate. These equations are the same. The bottom one is simpler and the top one maybe makes more sense intuitively. All right, and so what these equations help us answer is what happens to the bias and the precision of the AONR when we leave out each nitrogen fertilizer rate from the trials. Now there's going to be a little bit of audience participation. I won't make you raise your hand or vote or anything on what you think is going to happen, but I have some options. And you can pick one, and as we go through the presentation, we can see if you're right by the end. So our first option is maybe this control rate has a disproportionate impact relative to other rates on the precision and the bias. Maybe it's less important than other rates. So maybe these on-farm trials are onto something. We're like, oh, we don't need to measure these ones that aren't close to the optimum. Maybe they're onto something, which would be great. Maybe all rates are equally important and dropping one has the same effect as dropping any of the other ones does. Or maybe leaving out the rate that's closest to the estimate has the greatest impact. So if your optimal rate is 225, maybe dropping a rate that's 220 is going to really increase your bias or your precision. So those are your options. Pick 1 through 4, and we'll come back to it in a few minutes. So the data set that we have access to analyze this data comes from Curtis Ransom. The citation is there, and it was a collaboration between Corteva and a bunch of research institutions covering a bunch of states in the Corn Belt from 2014 to 2016, and they've got those 8 treatments from 0 to 315 that I've been showing. So I'll go into what we saw at some specific sites, and then we'll go into some overall summaries. So here's a site that we measured that has positive bias. So this is showing when we analyze it with all of the data. So we have our nitrogen rates on the x-axis and yield on the y-axis. And when we fit the quadratic plateau model using all of the data, we get an AONR of 125 and a standard error of 11.8. And these are 95% confidence bands shown here. So when we drop the rate and we refit the model and calculate the AONR, we get a different number, 176. This gives us a bias of 51 kilograms of nitrogen per hectare, which means that if a farmer were to get an estimate using all the data without the control treatment, he might be over applying his nitrogen by 51 kilograms per hectare, spending a bunch of money to get no increase in yield. We also see that the change in the standard error is 155% as those standard error bars get much wider. We also had some sites where we saw negative bias. So here, when we use all 8 rates, those red elements again, we get an optimal rate of 133 kilograms per hectare. And then when we drop that rate, fit the model again, and calculate the AONR, we get 98. So this is a negative bias of 35 kilograms per hectare. And if this farmer were to make a decision without the based on the data without the control treatment, he'd be under applying by 35 kilograms of nitrogen per hectare, meaning he could have applied more and gotten higher yields. And we also saw an increase in the standard error of 70% at this site. And then finally, we did have some sites that had near zero bias. This site specifically didn't have any, where it didn't really matter if you had the control treatment or not. The bias was 0 and we got the same estimate either way. However, the uncertainty associated with that estimate, the noise, increased also by about 70%. So those are individual sites. What did we see overall? Maybe one of those was happening more frequently than another. So there's a lot here. I'll break it down. So the box plot on the left shows the AONR when we use the complete data set, when we use all 8 rates. And then the dropped treatments are, so when we drop the N0 treatment, drop the control treatment, then we calculated the AONR. When we used all of the data, we achieved an AONR of almost 200. And that orange line is just extending it out so we can compare it to the subsets. And we can see that there's not a huge amount of bias. We're seeing the most when we lose the control treatment, but it's not a statistically significant amount because of how much variability there is throughout all of these data. However, as you may have picked up on the trend previously, we lose a lot of precision when we drop the control treatment. So again, we have our dropped treatments here. The complete data set's not shown because the change from the complete data set to the complete data set is 0. But we see that when we drop the control treatment, the standard error increased by about 40% on average, which is statistically significant and also the highest amount that we observed from all the other treatments. I'll also point out that, so our optimal rate when we used all the data was about 200. And if we look at the 2 rates that are closest to that 200 value, that 180 and 225, when we dropped those treatments, we didn't see much change in the standard error at all. So we observed this, this bias at individual fields that I showed before. And one of the questions that one of the co-authors had on this paper was, can we predict the direction of this bias? Maybe there's some characteristic of these sites that if the value is low, we see negative bias. If it's high, we see positive bias, some sort of relationship like that. Maybe it's organic matter, where if we're not applying nitrogen, there's a lot of organic matter in the soil that's high in nitrogen that's biasing our results in a certain direction. Maybe the water content is messing with the nitrogen cycle in a certain way. Maybe the sand content. We threw a lot at this to see if we could predict it. We analyzed the data by soil horizon, by depth. We looked at individual states to see if they had any trends or if there was a trend by year. We looked at a lot, and the answer is no. We could not predict the bias. So this would have been really cool. It would have been really interesting, but it kind of just reinforces the need for measuring something that we can't predict. So if you were following along, if you picked an option, number 1 was the correct one. So if that's the one that you picked, if you're in my lab, you should have. Then congratulations. All right, so conclusions from this chapter. Excluding the control treatment led to less precise estimates of our AONR. This is also more impactful with fewer rates. So our experiment had 8. In those on-farm trials where they have maybe 4 or 6, if you don't have a control treatment, you're really going to feel it. I did some simulations where I just had 5 evenly spaced out rates. And when I dropped the control treatment, I saw a median increase of 133%. So that's not even the mean, that's the median, which is a little bit more robust to outliers, and it still increased by a ton. And it was also harder to even fit a model to that data. So you would be getting no value out of your trials if you do that. And so a question I would pose to people doing these experiments is, what would you give to reduce your error? A lot of people are doing really complex modeling, spatial modeling, variable rate technology, satellite images, things like that to try and make their estimates more precise. And this seems like a pretty easy one for me to really reduce the precision or increase the precision, decrease the error in your estimate. And so tying back to the title of my chapter, if you lose the control treatment, you lose control of your estimate. Okay, now we'll get into the next chapter where we introduce the quadratic-plateau-quadratic model, capturing the ups and the downs. So this is an example of one of the sites I just finished talking about from our nitrogen trials, where we see an increase in yield as the fertilizer rate increases. But then these last couple rates, especially this last one, is maybe going down. And so the question we have is, tying back to the theme, is this signal or is this noise? Is it just happening randomly, or is there some cause that's causing a decrease at these high rates? Now, if you know a lot about the topic, then that might help inform your decision. Some ideas that I have that could maybe be causing this is maybe your crops are lodging, so you're getting a lot of vegetative growth with high nitrogen, and then they're falling over and you're not able to harvest the yield at those really high rates. Maybe there's some nutrient competition going on in the soil, toxicity levels in the plant. Maybe you're disrupting the soil microbiology that's harming the crop's ability to generate high yields, something like that. So is this signal or is this noise? I don't know. But if it is signal, we should model it. And to the best of my knowledge, we don't have equations that identify what that value is where we start losing our yield. So that's why we developed the quadratic-plateau-quadratic model. Our lab developed it. I characterized it and was looking for some trends and kind of wrote a paper to introduce this to people to make it easier to use. So what this looks like when we mess with our different parameters. So we have our intercept parameter, which as we increase it, it just shifts the whole model up. Our B parameter is the slope. So you can just see it gets steeper and the plateau is much higher as we increase the slope. The first breakpoint is we move that further out as the X value increases. That's the effect that it has on the shape of the model. And then as we increase that second breakpoint, that extends where it starts falling off, and everything else before then is identical. So now I've got an example of some of the fit statistics that we would see if we fit the model with our quadratic plateau and then this new quadratic-plateau-quadratic model. So we don't need to get into all the weeds with this, but the AIC value, lower is better. These are almost identical. So they're basically a tie. The R squared value, the higher the better. And these are, again, very similar. The optimal agronomic optimum nitrogen rate that we've been talking about, 111 versus 107, very similar, which I think is good that they're performing the same, because you don't want including that drop off at the end to impact how well you're estimating the optimal rate in the first place. And the standard error is very similar too. So we're still estimating that breakpoint with the same amount of precision. And then the second breakpoint occurs at 262 kilograms per hectare. Quadratic plateau doesn't have that. And then there's a little bit more uncertainty associated with that second breakpoint because there's less data at the end informing where it truly is. We also thought that this model might be useful over measuring variables over time. And so what we did was we took some NDVI data, which stands for Normalized Difference Vegetative Index. It doesn't really, like, if you don't know what it is, that's okay. It's basically the higher the number from 0 to 1, the more abundant and healthy the vegetation is. And so at the beginning of the season, it'll be really low. And then at the end of the season, as the plant senesces, it will drop off. But in that reproductive stage, in the adult stage of the plant, it should be much higher. And so then we converted that to leaf area index into light interception and fit the model here. We also fit just a quadratic model because it seemed like a pretty good substitute, something that we could compare the results to. And some reason why you might want to use this is let's say you want to your crops to intercept the maximum amount of light during the longest days of the year. So you'd want to time up your planting date with when that will be so that your plants can absorb as much sunlight as possible. Comparing the fit statistics of these models, again, AIC is pretty similar. Lower is better, even if it's negative. So we have a little bit better fit with our new model. The R-squared is very similar. The first breakpoint with our quadratic plateau model is a quadratic-plateau-quadratic, excuse me, is 190. The quadratic obviously doesn't have a breakpoint, but I just kind of said when it gets to 95%, that's like the plateau, we'll say. And that occurred at day 189. We had a standard error associated with the quadratic-plateau-quadratic model, and then where that breakpoint, the second breakpoint where it starts decreasing again is day 220. Again, using the below 95%, we got 223 with our quadratic model. So these are some of the results that you can get when you use this model. If you've got some data that you think this might be useful for, then I encourage you to use it. It's on Fernando's package in R. Okay, so we ran a bunch of simulations to try and identify some convergence criteria, to identify some categories, some characterizations of the data that will maybe tell you if this model will be a good fit for you or not. The first example shows some non-converging data, and we couldn't really find any like hard and fast rules of what's required of the data. Maybe it has to decrease from the plateau by a certain amount. Maybe you need a certain number of data points after the plateau. We tried a bunch of stuff and couldn't really get any hard and fast rules. So just some overall trends that I'll talk about. So this first one where it did not converge. Some reasons for that could be there's not really a clear plateau. It's really noisy at the top, and you're not really confident that you reached a plateau. There's also not a huge decline at the end saying, okay, yep, we're for sure heading down. We're decreasing here. We've reached a plateau. Our model also requires symmetry. So the rate that you increase to the plateau has to be symmetrical to the rate you decrease afterwards. This makes fitting the model a little bit easier. It decreases the number of parameters. And we don't see that trend here. So maybe that's a reason why this data did not converge, or the model didn't converge. This middle example is where we did get convergence, but we saw high bias. So our solid lines represent the true values we used when we simulated the data, and the dashed ones are the estimates. And there's not a huge plateau. I'm not really convinced that we reached one. And so those estimates got really squished together. So this would probably not be a great candidate for this model either. And then the last example is low bias. This one's a great one. We're confident that there's a plateau there, and we are confident that it decreased at the end, and it looks symmetric to the increase at the beginning. So conclusions from this chapter, if the decline is signal rather than noise, like we talked about at the beginning, if you really want to capture where that breakpoint is, this model will do that for you. Tying it back to the previous chapter, this model will also perform much better with the control treatment. The wider the range you have, the more likely you are to have precise estimates. Okay, moving on to chapter 4. Can you hear me now? Detecting a signal to predict corn yield response to phosphorus fertilizer in Kansas, USA. If you don't get the title, the picture maybe helps, and if the picture doesn't help, ask somebody older, maybe. But we're switching gears a little bit here. We're looking at phosphorus data in Kansas, still corn again. But to outline the problem that we looked at in this chapter is when people do these fertility trials, especially in phosphorus and potassium, they identify some critical soil test value, but then they see a lot of sites with a lower soil test value they would expect to respond don't respond, and sites that are above that critical value that shouldn't respond do. And so that's the problem that we're hoping we can address. And so we're asking, can we improve how this responsiveness is classified to make it more predictable? So they're saying, oh, my site was this and it didn't respond. Well, how are you measuring that? Is there a better way we can measure that maybe can decrease the amount of noise in our results? So how it's normally classified is with the ANOVA method, which in non-statistical terms is basically asking, is any treatment different from any other treatment? So if you have one really low rate and a bunch of high rates, you're good to go. You saw a response. This might accidentally classify responsive sites as non-responsive because it's not very sensitive, it's very conservative. And then our new method that we propose is this linear regression method, which simply asks, is there a trend? So if there's not a trend, you just kind of see a straight line. And what we did is we fit a linear plateau model, a quadratic model, and a quadratic plateau model to see if those models fit the data better than a straight line. And if they did, we're saying, hey, there's a trend here. Your yield is responding to the fertilizer that you're applying. This has more statistical power, so it will detect smaller differences. But because of that, you might accidentally classify sites that aren't responding as responsive. So those are kind of the two ways you might fall off in either direction with these methods. So the method we used, so we're asking about predictions. So we have to make predictions now using both of our classification methods and see which method performed better. And so the methods that we used are logistic regression, elastic net regression, and random forest. So logistic regression is the simplest one. It's easy to interpret, but it can be very difficult because we have a bunch of predictors, which I'll get to in a minute, and you build a model with your predictors, and there's no guarantee that you got the best combination of predictors to get the best model possible. And with elastic net regression, it helps with that process. So it works really well when you have a lot of variables. If they're highly correlated, it simplifies those down, which we have a lot of highly correlated data. A lot of soil values are highly correlated. A lot of the weather variables that we'll get into are also highly correlated. And so that was a strength of this method. And then random forest, which is known for its predictability. It's a machine learning technique, and it's the most complicated one. And so these are the methods that we use to evaluate, that we use to predict whether sites would respond to fertilizer or not. So the variables that we used, so we're interested in predictions, and so we can't use data that we know at the end of the growing season, obviously, or during the growing season, because you have to make a decision to fertilize at the beginning of the growing season. So the variables that we know ahead of time are management variables. We have a bunch of soil measurements from soil tests. We don't know the weather for the current year, but we know the history. So we can get 30-year averages of different climate variables. And then we know the location, latitude and longitude, to see if those have any trends. So this experiment was done in Kansas, and the experimental design is in this bottom right corner here, where they all received some nitrogen rate just to make sure that nitrogen wasn't limiting the response, because then if a plant doesn't have nitrogen, you apply a bunch of phosphorus, it doesn't matter because the crop needs nitrogen. And so you're not going to see a response where maybe it would have responded to phosphorus if it had enough nitrogen. So that's what that's all about. And they applied 5 different rates of phosphorus. And then I've classified here the individual locations in their responsiveness categories. So the red ones didn't respond to either method. The green ones responded to both methods. And then we had the yellow sites, which responded to our more powerful linear regression method that didn't respond to the ANOVA method. Now, I'll point out here, there's not very many responsive sites, and they're very clustered together, which means they share a lot of the predictor values that we're trying to predict. And so that kind of spells trouble. So we had 23 sites that were non-responsive. I pulled examples of each category so we can get an idea of what's going on. And you can see with the non-responsive sites that the best you could do is probably draw a straight line, and you can't say with any confidence that the yield when you apply 120 kilograms of phosphorus per hectare increases your yield at all. And then our yellow sites, we can see that there's a positive trend where as we increase the rate, we get higher yields. But if you were to run an ANOVA on this, it would say it's too noisy. They're all pretty close together. We can't definitively say that one is different from another. And then when it's responsive to both, that even the ANOVA method will pick it up. We can see when there's no phosphorus, the yield was much lower than when more phosphorus was applied. So we're going to look at the combination of the classification method and these three prediction methods in our next few slides. And the results will be shown in what's called a confusion matrix, where we know whether they responded or not after we've collected the data. And then what we do is when we make our predictions, we'll create a model using 32 of our 33 sites. We'll leave one of them out. And then once we've created the model, we'll use the data we left out and predict whether that will respond or not. And then we'll put that one back in and we'll take the next one out. We'll create a new model and make a prediction for that next site. And we do that until we've left out every site once, excuse me. Some of the terminology, the metrics that we use to evaluate performance is accuracy, which is just of all the sites, how many were responsive that we predicted responsive, how many did not respond that we predicted would not respond. But we also wanted to look at other metrics as well, such as sensitivity, which here it's for the sites that actually did respond. How often did we accurately predict them? Now, an example of a model that is not very sensitive would have a lot of false positives. It'll label everything as positive. It'll say everything is awesome. So it'll, even if you have sites that aren't responsive, it'll say, close enough, you responded. Great. We also will measure specificity, which for the non-responsive sites, how specific were we in identifying them as non-responsive? This is the true negative rate. And if we have a model that's not specific, it's very likely to classify things as non-responsive. So you can bang on the glass, you can yell at it, you can show it a really responsive site, and this model is just going to sit there and not move and say, nope, not responsive, doesn't count. And then the last thing we'll look at is balanced accuracy, which is just an average of sensitivity and specificity. So the perfect balance between the two. Okay, and so this, getting into the models that performed the best, this one had the highest accuracy, where our accuracy was 85%, where we correctly predicted 28 sites, which is pretty good. But we predicted that nothing would respond. So we're getting that result there, where the sensitivity is 0, the specificity is 100, and because of that, the penalty associated with those things, the balanced accuracy is only 50%. The one that had the best performance in other metrics was with our new linear regression method, which was exciting, when we fit it with a logistic regression model. We correctly predicted 26 of the 33 sites for an accuracy of 79%. Our sensitivity was okay, our specificity was lower, but overall the balanced accuracy was 74%. And the variables that we had included in this model that performed the best, that predicted whether a site would respond or not, were the pH, which is it's involved in a lot for people not knowledgeable about soil fertility. pH is like the master variable. It's involved with everything. Olsen P is a soil test, so that's exciting that was in there. The sulfur amount of the soil was in there, electrical conductivity, the seeding rate, so how densely you plant your seeds, latitude, how far north you are, and then the July historical average minimum temperature. So I was glad to see that we got a weather variable in there. And this was the one that did the best job. We could substitute it with a highly correlated one and get a similar result, but this was the July minimum temperature is the one that did the best. So results from this chapter, the ANOVA random forest method did have the highest accuracy, but it's maybe not the most useful model because all you're just going to do is just tell everybody to never apply phosphorus again. So maybe with the other performance metrics that we evaluated, the linear regression, logistic regression method was the most useful for making some predictions. some speculation on my part. I think if we had more responsive sites and more variation among those responsive sites, that would be really helpful, especially for the random forest method. It's very data hungry, data intensive, and that would really help that method a lot. And again, I think that the results would be worse without control treatment because you'd be less likely to be able to identify responsiveness. Okay, now this is the slide where I put everything, all the big main conclusions from my entire PhD time here at Iowa State onto one slide. So number one, from chapter 2, use a control treatment. Number 2, we introduced a cool new model. If it makes sense to use it. Hopefully it's useful. For people that are trying to classify responsiveness and make predictions, consider our linear regression method, and you can use the framework that I discussed to generate predictions using these different methods and these different performance metrics. And with that, we're at the end. I have a bunch of people to thank. Number 1, I'd like to thank Fernando for being my advisor and emailing me all those years ago after I stumbled through his crop modeling class. He said I knew enough and did what was expected of me. So yeah, thank you for mentoring me and teaching me how to be a better writer, a better thinker, a researcher. I've really learned a lot. And thank you to my committee for being here, for being my professors in my classes, for being co-authors on some papers, and for mentoring me along the way and encouraging me when I got some responses from reviewers that were a little tough. Thank you to the National Science Foundation for some funding when I was doing my graduate certificate. Thank you to my lab group. You guys get the first draft of everything, the worst draft of everything I've written, all the presentations and the posters I've made. And every award I've gotten, every presentation I've made is better because your guys' input has been included. So thank you very much. I'd also like to thank my family and my friends for being here and for supporting me along the way. And most importantly, excuse me, to my wife, Morgan. She's encouraged me and believed in me more than I deserve. And I couldn't have done any of this, and I wouldn't have done any of this without you. But thank you very much. And I'd be happy to, once I collect myself, take some questions. Thank you very much.
Questions from the audience?
Victoria.
Great presentation, Alex. Something that I really like about you is that you work with very difficult topics and things that for me are all new or were new when I came here. And you always try to find a way of making it more easy to understand for people that are not familiar with the topic. So that is very, very, very nice about you and your way to work. And something that I was curious is that before you develop the Quadratic model, if you use that model in the same sites that you used first in your second chapter, and if you were able to use it, if the accuracy and precision they change when you apply this new
So the question online was if I use the Quadratic-Plateau-Quadratic model in the data for the second chapter. The answer is no, we did not. I think because the interest was in the optimal rate, finding out where what the like toxic rate or excessive rate is wasn't of great importance. We're more interested in the experimental design associated with the quadratic plateau model, which is like one of the most commonly used ones, as opposed to like this new model. I imagine we would see similar results where you would lose precision in the first breakpoint if you were to fit the quadratic plateau quadratic model to more of the data.
I think, Alex, you might not remember, but you've done so many things. But that chapter 2 had like 40 some sites.
846, yeah.
46, and at one point you did run the Quadratic-Plateau-Quadratic to all of them.
Mm-hmm.
And they were maybe a handful, less than 5, 3 or 4 that you were able to fit the Quadratic-Plateau.
Yeah, the convergence was pretty bad.
Well, yeah, there were just a few that were it would work. So it wasn't worth like doing it for all the data set, but there were a few where there was a drop at the end.
Yeah, I was imagining that maybe you were not able because you didn't have that drop in the.
Right, exactly. Yep. Yeah.
Great presentation, thank you. So I'm just curious, in your control treatment, it was always 0.
Yes.
Does the control treatment always have to be 0? And would that change your answer if the control treatment wasn't 0?
Could you give an example of what that treatment would be if it wasn't 0?
Well, I'm just, the word control doesn't always have to be 0, does it?
Yeah.
Am I wrong?
It doesn't have to be. So some of the data we had received like a base amount of nitrogen at planting and the rest applied as side dress. And so maybe you could consider, if you applied 45 kilograms per hectare at planting and then none at side dress, maybe that's your control treatment. We had data like that, and we just looked at the total nitrogen applied. You could look at the data differently. I'd be speculating on what I think would happen. I think the more data you have informing the quadratic function of the quadratic fraction of the quadratic plateau model, the better off you are. And so your results would maybe be better if you had a true 0, but if you don't, then if your control treatment is some non-zero value, I would still think there's a lot of value in it. Yeah. Yeah, Kyle.
Alex, so in chapter 2, you talk a lot about the economic optimal nitrogen rate. A lot of times people look at the economic part of it. Would you expect to have the same increase in standard error in the economic optimal nitrogen rate as you did in the agronomic one, or not?
Yeah, that's a really good question. So for the people online, the question was, we were looking at the agronomic optimal rate, but what a lot of people are interested in is the economic optimal rate. So that takes into account the cost of nitrogen, because you might get an increase. Let's say you apply $20 worth more of nitrogen and you only see a $10 increase in yield. That wasn't, you shouldn't apply that much. You're not getting the money out of it. And so people are interested in this economic optimum rate. I would expect it to be lower. I would expect the standard error to be slightly narrower because it's lower, but I think our overall trends would would persist, and we would still see that increased impact with the control treatment.
Thanks.
Yeah. Are there questions online?
Are there questions online? I don't know if they can hear. I don't see anything in the chat.
I hope they can hear. Yeah, I'm not doing it again, sorry.
Last chance for online. I don't know if they can hear me.
Oh, you don't know if they can hear you. Okay, if there are any questions online, go ahead and type them in the chat. I think I have you all muted.
I'm muted, but I don't want to be. It's going to cause echo of you.
Yeah. Chat looks empty.
Yeah. I think it was 100% clear. That's why.
It's very kind of you.
There's no noise after this. Silence.
Sean.
Great presentation, Alex. For the drop off in the quadratic model, do you tend to see that more pervasive with certain crops versus others, or is it known whether that's only for one type of crop?
So the question was if we see the decrease with the Quadratic-Plateau-Quadratic more commonly in other crops. We only looked at corn, so I can't say for sure. It could be different for different crops. It could be different for different nutrients. So I think it'd be something to look into. And yeah, if there's people that have data like that, I encourage them to give it a shot.
So there's a question from Bradley in the chat, and he's asking, I think he's referring, to the third chapter, and how many of those variables were measured versus estimated from a database or sort of.
Yeah, so I'll repeat that online just for people. Bradley in the chat, Dr. Miller asked, were all your soil properties measured, or was soil survey information ever used in any of the cases? All of the soil properties were measured. They were collected and aggregated and sent off to a lab for analysis. They did not use the web soil survey for anything.
The weather variables are taken from the weather station.
Yeah.
National Weather Service weather station.
Yeah, the weather variables were from the weather. We used the Iowa Mesonet to extract the weather variables from the nearest weather station.
Any other questions from the audience online? There are no more questions. Let's thank Alex for her presentation. This is the part where the fun starts. With the committee, thanks everyone for coming. You can take something on the way out if you want.
Yeah, please do. I don't know if anyone touched any of the snacks, so have some breakfast.
Yeah, let's take a 5-minute break for the committee.
All right, thanks everybody for attending virtually.
Yeah.